Welcome back. Any questions anybody has about the discussion we had? Yes, ma'am.
Sir, in previous discussion, we just trying to say that crispy and crunchy differentiation. So I have a perspective that what I have learned in my job, that what I bite in the front teeth that is crispy, and from here it's crunchy, and from here it is brittle. So can we differentiate it that when the as crispy is low, hardness is very less. So from that cut we can differentiate that it is crispy, and when the hardness peak is little high, then it's crunchy, and brittle the hardness level is more high. So it's brittle. Can we differentiate it like that?
The question here is from the sensory point of view, not you, sensory point of view, there is a way you can differentiate between crunchy, crispy, harder, softer, like that. Can we can we divide this texture profile into different regions? Huh? Yeah, depending upon the force, can we do that? Anything can be done. Um, Let me go back to the texture profile graph here. So according to Moshimi, what she is thinking is, now that we got the texture profile here, can we say that this is, let's say the deformation is some number here, and then 10% is, if we take a 10% of deformation crispy, like that? No?
Saying that if this is the sample A,
Yep.
if we take another sample and its curve, the peak is not like that. It's somehow it's low. Then yeah, like that. It's a peak is low and a peak is high. One is in 300 and another is in 600. So on that basis, we can differentiate like that. That the 300 something is a region is that is crispy, and over that is crunchy, and over that is brittle like that.
You can do that, but at the end of the day, is everybody understand what she is talking about? Okay, you all hear that. Okay, I don't know how to repeat that. So at the end of the day, you need to understand, is the sample A and B are similar, are the same source of information, are totally different samples, things like that. If you are comparing different chips, then that would make.
Another is the kurkure type of thing. Wafer is very much like it's not so much hard, and on perspective of kurkure, that is a little hard than the wafers, normal wafers. So that is
Yeah, but the issue there is you may not be able to do a texture profile analysis for both the samples. With yeah, we can get only one peak. So how do you differentiate there? That's also issue here, right? And on the other hand, so that's why I said that this profile analysis cannot be objective test. It will be subjective test. So when you go to that kind of minor, when I say minor, okay, let's think about, I mean, we can come back and in the afternoon we'll talk more on that also when we talk about sensitivity analysis. As a human being, our brains are more powerful. We can differentiate a lot of things. As an instrument is something, we tell the instrument this is how you think about these things, and then it repeats it over and over again. That's a good thing about instrumentation. Bad thing about the human being, we keep changing our perception, we keep changing our ideas. We say one thing, when time comes, we reverse the whole thing. We say, no, I don't want to do this way now. I want to do something different. This is how I want to do it. See, with that only, that's why it's become subjective. Today I may say, I like this ice cream. Tomorrow, things changes. Same ice cream, I will say it's a bad ice cream.
That's why I try to develop
So that's the nature of the human being, right? But at the end of the day, human beings are consumers. And the consumers are going to do the same thing. They are not going to be anything different than they are human beings. They are going to do the same thing. That's why industries keep changing their products. How many years they can live with the same product? Because consumer want newer product. It's not about the product anymore. It's about the packaging a lot of times. Huh?
Packaging and taste also.
Well, taste also keep changing, right? Today I may like the ice cream today, tomorrow I may not like the same ice cream because my perception changes and I am in the driver's seat as a consumer and I have a choice to make because I'm going to pay for the what I'm going to buy, so nobody can control me, and that's a sad part of it. And with the technology and all, it's not getting any better. It's much more difficult for the industry to survive, and and consumers are uh, consumers are driving everything, and then they are demanding a lot more than they don't even think about anything else as a consumer, including me. If I demand something, I want it. Everybody like that. So that's the sad part of it. But irrespective of everything, life goes on. Industry is still there, and still they are making product. They are still selling stuff. We are still buying things. We are still throwing things, right? So when you think about the whole thing, at times I think that are we justifying our presence no matter how much money we have, how much we are wasting? When you think about that, it's very, very sad. I mean, when you think about that, I mean, people have money, but money may not make everything. But at the same time, we cannot worry about everything, right? If we worry about everything, nothing can be done. So it's a lot more complex than we want to make it, but it's what it is. I mean, at least we have tools to use it for whatever scientific knowledge we want to gain, and that's what it's important, in my opinion. Very good point. Okay, let's go back to our functional properties. Okay, so far we talked about different properties: elastic properties, mechanical properties, viscous properties, viscoelastic nature, texture profile, all those things. Let's take a break from that technical stuff, objective things. There are a lot of other things happening with the products. One product is I have worked with this product many years. My favorite product is cheese. I worked with the cheese for 10-12 years now, more than that. And as much as we want to study the texture of the cheese, viscoelastic nature of the cheese, those information are more useful for product development. But when it comes to the application of the cheese, where do you apply the cheese? Pizza, exactly. We talked about yesterday also, right? Pizza is the main ingredient, main staple food now in mainstream, right? Compared to idli, dosa, roti and things like that. Now it is mainstream is burger and pizza like that. Things changed in India, but even in US, still mainstream is pizza. Many years. Pizza and all came to US, came to India from foreign countries only, right? Eastern European countries and US and all. But still in US, pizza is the primary thing. Burger is the primary thing. How long that's been going on? I'm sure it will be there forever. It's not going to go away anytime soon. It cannot, because there are a lot of players in the system. They will make sure that people keep eating pizza, keep eating burgers. Whether it is good to eat or not, that's a different story. That is consumer choice. They will make the decision what they want to do. So when you think about the cheese, how it is employed? Cheese is employed primarily in the pizza and not in the cold form. Pizza need to be cooked it needs to be baked in the oven, and then it has to be, the cheese is the main ingredient, right? If there is no cheese, it's not even called pizza, right? Anybody will eat the pizza without the cheese? No, right? Main ingredients is cheese. Without the cheese, that's why I call main ingredients. But if you look at the total volume of the pizza, cheese is probably only 10% or 15%. Not even that much sometimes. Sometimes they mimic a lot of things, so real cheese may not be there. So only few percentage of real cheese will be there. But again, whatever it is, it's what it is. You need to satisfy the consumers. So cheese main functionality is the how it melts. You can bake the dough and then you can apply sauce and you can put the cheese on it and then serve to the people. Nobody will eat it, right? If cheese is not stretching, if it is not melting, if it doesn't cover the whole pizza, we eat only part of pizza which has a cheese melted properly and it is stretching. Correct? How many of you eat the crust of pizza? No, we don't, right? No way, Jose. I mean, if cheese is important and cheese needs to be served properly. I mean, cheese doesn't have to be heated. I mean, because it's processed product, you can eat the cheese as it is. It doesn't have to be heated. But the functionality is that cheese needs to be melted and it has to have a stretching properties. Without that functionality, it doesn't have a value. Make sense? So how do we evaluate these melting characteristics? How do you evaluate the stretching characteristics? Things like that. How do you do that? Any thoughts? I mean, product development is important, right? They cannot just like to put the cheese without knowing whether cheese can melt and stretch and things like that. Without that information, not just putting the cheese only, it's not going to help them out. Because when it goes to the oven and then comes out getting served for the consumers, if they are not going to eat it, then they are going to waste. So what do they do?
At what temperature it is viscoelastic and what's the viscosity? It is ductile or not?
Okay, again we are going back to the more reological way of thinking. But that is more than that, right? Because we are talking about functionality here. Correct? Because the base is different here. Even if you measure the viscoelastic nature of the cheese at different temperatures, heating conditions, what is that going to tell them? Again, it's going to give them the viscous modulus, elastic modulus and numbers like that. But they will not be able to know how much spread it has, how much it can elongate, things like that, right? These viscoelastic properties we are trying to measure may be useful to have for scientific knowledge, but in terms of application wise, how do we do that? Any other thoughts?
How much strain it can handle before breaking?
Correct, but that is primarily in the room temperature, right?
At a particular temperature when it is baked or
Okay, now what we are talking about is, so far we talked about solid samples, right? Cheese is a solid sample, well, semi-solid, mostly it's solid, some viscous nature is there, but it doesn't have to flow, right? It can be just like that solid only, right? You can cut the cheese cubes, things like that, slices like that, put it in the refrigerator, it's going to stay there, right? It's not going to just like that melt. So if you are going to put it in the oven, it's going to melt. It's going to deform without not even applying any force at all. Temperature is going to dictate things. So there should be a way to measure how much it melt at different temperatures. Right? That's one way to evaluate the functionality of the cheese, dairy products. Make sense? Right? What is the temperature of the oven? The cheese preparation, not cheese, pizza preparation. What is the typical temperature of the oven? In degrees Celsius? 180 degrees Celsius. Give and take, 180 degrees Celsius. What will be the temperature the cheese will go up to? It cannot go up to 180 degree, right? Can it? It will go beyond 180, even though the oven is at 180. Okay. 180 degrees Celsius. If you put the cheese at 180 degrees Celsius, what will happen to the cheese? You get the burned out cheese. You are not going to eat it, are you? No. When you think about that, the heat transfer from the oven, conduction, heating coils, heat is going to transfer through the convection, going to the cheese, and the maximum temperature it can reach is 100 or 110 degrees Celsius. That's the only way you can get the golden brown cheese. Otherwise, what you get is, what is that?
Black
Burned cheese. Nobody is going to eat that pizza. Think about that. The oven is 180. It has to be 180 only. But the cheese temperature will not reach more than 100 or 110 degrees Celsius. If you start bubbling and things like that, it gets hardened, it comes out as a black cheese or burned out cheese, people are not going to eat. The pizza cheese should be golden brown. If it is not golden brown, people will throw it, or they will probably call the same driver, delivery person, saying that, return it back. I don't like your pizza. Much easier. Or call the store and tell them that no, we don't want the cheese. We don't want this pizza. It's not up to the mark. I'm not going to pay for it. I will report to my credit card. I will get refund, and then take it back, including the tip also. Give it back. Because we are hungry. We want to eat the pizza. That's why we ordered. It's not delivered properly. We are mad, right? So in actual functionality, the cheese softening and melting is very important. And this is what we are going to talk about this morning, about how do we measure these properties? What are the different ways we can do that? So basically, the meltability refers to the ability of the cheese to flow caused by the heating, while free oil releases the tendency of free oil to separate from the melted cheese. At the same time, you don't want to have oil oozing out also. You want cheese to be heated, but no oozing of oil, right? Because if it is oozing of oil, it's very, it's not appealing. If you see a lot of oil, we are not going to eat it, right? We say, oh man, what is this? I want only cheese, golden brown cheese. I don't want to drink this oil, right? So there are a lot of challenges here. So it's the most important functional property for use in prepared foods, but there's still no formal definition. Definition wise, could be that ease and the extent to which the cheese will be flow and spread upon heating. Some of the cases, cheese that softens but not melt and flow are needed. One prime example is burgers. There, you don't want to see cheese coming out at all. You just want to see cheese softened, stay there with the meat, whether it's chicken or what is that? bun, and then whatever the meat or whatever chicken or other things, the
lettuce,
no, no, not lettuce, in terms of replacement for meat. If vegetarian people,
paneer,
paneer, yeah, paneer or whatever you have, so they want to make sure that it is conforming to the form. It's in this form. You don't want to see that coming out and then getting messy and things like that. The softening of cheese is important. Melting of cheese is important, more specifically. So long back, when they developed the dairy products, more importantly cheese, there was a person called Schreiber. Um, Schreiber was a scientist in one of the biggest dairy industry in US, and he took a piece of cheese sample, about 5 gram cheese piece, circular piece, and he took the petri dish and he put the piece of cheese in the petri dish and put it in the oven that was set at 180 degrees Celsius, because that is the condition the pizza oven works. So you put it there 180 with the petri dish and cheese in the petri dish, and then he heated for 5 minutes or so, took it out. After it's cooling down, he measured the area, and then he called it as a Schreiber test. So we thought that is overkill. So we were trying to find out, is there any other way we can reduce the heating, we can use the different surfaces so that it has a better spread. Bless you. So basically you are looking at the spread area, maximum diameter. So we tried different surfaces including petri dish. What you see here is aluminum plate, and that gave us a better spread out of all the things we tried. Stainless steel, aluminum plate, iron plate, you name it. There are about 7 or different plates we tested out. Aluminum plate gave us the best spread of cheese. And then temperature wise, we tried different temperature up to 110 degrees C, because we measured during the pizza making what is the temperature cheese reaches. That's about 100 degrees C. So we tried 80 degree, 90, 100, 110, and 90 degrees C is the best temperature we thought it will work best. So that is the picture you see, golden brown cheese, 90 degrees C, less energy input, you were able to get maximum spread. And we used this image analysis. Previously what they did was they were doing the circles, because some of the cheeses will not be this uniform. So it could be like that. So they trying to measure the diameter of the circle. We thought that doing the area measurement will be much more meaningful, and that's what we found out. And we published a work on this one, published a paper on this one. So it is a very simple method. You take a piece of cheese, 5 gram cheese, a disc, put it there, 90 degrees C oven, put it in the aluminum plate for 5 minutes, you heat it and take it out and measure the area. That's one way to measure the meltability of cheese. If it is a low melt, you will get a less area spreaded out. So that gives you the higher spread, that will be the best option. So from that you can differentiate between different cheeses. Then you can modify your processing parameters to get a better spread. That's one way to do that. Any questions on this simple method? All we are trying to do is how well the cheese can spread. That's the bottom line. This may not be the actual application. If you really want to do that, you have to put it under the pizza dough and all the toppings and everything, but may not be needed. Even if you do the same thing, you probably get the similar results. So this one is much simpler, and that's what we did. And we are still using this method for evaluation of different cheese products. Okay, the next method we developed is it's called melt to profile test. It's like this, similar to texture profile test, texture profile analysis, and this is a melt to profile test. This is the method we developed in our lab when I was doing my postdoc in UW-Madison. The idea behind this test is primarily you put a piece of cheese disc and then put it between the two plates, and there is a LVDT. So, and then you put the whole thing in the oven, whole setup in the oven, and then you have a thermocouple going from cheese and the center of the cheese and connected to the data acquisition system. And this LVDT differential transducer, it's also connected to the data acquisition system. So it collects both the cheese temperature and also as cheese gets heated, it's going to slowly flow. It's going to spread. While spreading, the LVDT is going to go down. So you will know decrease in height and also temperature increase as you heat the sample. So you are collecting both information, decrease in height and the increase in temperature of the cheese. Simple setup. You don't have to do a lot of manufacturing things. You just need to have LVDT and the stand, support system and two discs, and then there is a rod inside that's connected to the top plate, circular plate, and the bottom is another plate like that. Any questions on this setup? So a very simple method, and then you can get the two different information: height decrease, melting, how the flow decreases, and then you measure the temperature also. So this is the data you collect. So height is decreasing, there's a pink line, and the temperature of the cheese is keep increasing from 10 degrees Celsius to 60 degrees Celsius. The temperature, the number may be different for different cheeses, depends upon what kind of cheese it is, what kind of functionality it's going to go through. So you get this. So from this, we thought there are three regions here. Initially, slow melting region, and then in the middle there is a flow is happening, and at the end not much flow is happening. So if you draw three tangent lines to the data, you get separate regions. So this is the softening region, and this is the melting region, and this is the post melt. So if you have these regions connected, then you can go here, take this point and get the temperature numbers. So this will be the softening temperature, and this will be the melt temperature. So, and then you can also look at the flow rate like that, because this is deformation, it's happening here, this is deformation happening here. So there is a lot of data you can collect from this raw data, and from that you can differentiate the different cheeses when you are doing the product development. So if you have a cheese which flows much faster than this cheese, that will have characteristics of this like that: faster moving cheese, melting cheese, slower melting cheese like that. We also published this work, and we are still using this type of test for testing different cheeses. Any questions on this test? Again, this is called melt profile. You can collect a lot of information from this, which is similar to the texture profile analysis. There it's double bite, but this is just a simple melt test. As you heat the cheese, how cheese flows, how cheese, the temperature increases, and this kind of information can be used for the product development. The next one is meltimeter. as name implies, again we are trying to measure the meltability of cheese. Nothing different here, same thing, but this one is much more user friendly. Once you make this system meter working, then it's user friendly. Basically, what you see here is the melted cheese. So here, if you look at this system here, what you have is the just a metal disc kind of thing, and there is a well in the middle, and you take a piece of cheese and you put this in this well, and then there's a lever. So you heat the cheese to the temperature. Once the temperature reaches that melted temperature, then you activate this lever and the cheese comes up, and then you have the top disc, it is on top of that. So as the cheese flows, you just follow the flow of cheese with respect to the time. So it's a controlled heating, uniform temperature, the cheese flow monitor, and the computer acquires the data. At the end of the day, you get this kind of characteristics. So as time increases, sample height decreases. So this is for two different samples at two different temperatures. This is low fat cheese, this is high fat cheese. So this is curve for this 60 degree C, and then this is for the 40 degree C. So as you see it here, low temperature, low flow, and low fat also. So the red line is the low fat cheese, low temperature heating. Black line is high fat cheese, low temperature heating, and green is the low fat cheese, higher temperature, and the blue one is the high fat cheese, higher temperature. So the characteristics we got follow what was expected. The trend confirms what is expected, because high fat cheese is supposed to be melted faster, and then higher temperature cheese will be melting faster also compared to low temperatures. So we took this information and we tried to develop some objective measurement here. From the height, you can follow the strain rate, shear stress, strain rate, and calculate the viscosity. That's what we did. With respect to time, from that information, we calculate the viscosity with respect to strain rate, because it's all about the flow. So from the deformation and shear rate, strain rate is how much, and corresponding viscosity we calculated, and that's what you see here. So force against causing flow and strain rate, cheese viscosity calculated in Pascal times second. So low temperatures, low fat cheese had a higher viscosity compared to the high fat cheese and higher temperature. And this is for the constant force, 0.7 newtons we applied. Basically that's because of the disc we used. This is 0.7 Newton. So this kind of profiles you can create. So if it is really fast or high melt, bottom right corner, low melt will be upper right corner. So if we have something here that will have a low melt, this is high melt cheese. So this kind of profiles you can develop for different type of cheeses you may develop down the road, or whatever industry is planning to do. We are looking at the two different applications, because the higher softening point or higher melting we want for the pizza. So this is where we will be looking at. On the other hand, if you are looking at if the consumer is thinking that I don't want to have a higher melt, I want to have lower melt, so that that's what my preference is. Then accordingly you can select the cheese. But at the bottom line is, when you make the cheese pizza using this cheese, they will be experiencing higher temperatures. So all your things will be in this region. And you can use the same information for providing cheese for your burger and all. So in burger case, you don't want to have high melting cheese. We want a softening cheese which will be better application in the burgers.
Sir, both the instruments, they will produce the data in the form of graph, or it will give the numbers, will get the graph. So this
Yeah, I mean it all depends upon how well you want to take this, what next level you want to take this information. Right now, these are all, the data is collected in Excel sheet, and then we create these graphs and all by ourselves and do manual calculations.
it is attached to the desktop. We can get the data just like it is.
Exactly, yeah. It's attached to desktop, and then the data is converted, put it in the text mode, and then you get the raw data and then put in the Excel, and from there you can do other calculations in the Excel, and then you can plot them and then use it for whatever purpose you want to use it. In US, a lot of industries, they use this multimeter thing. We have produced almost 13 different multimeters like this, same thing, and they have been using it in their labs for their product development work. Okay, next topic for discussion is stretchability. How much the cheese can stretch? What are the ways we can measure the stretch? Any thoughts? Tensile, okay. So basically, stretching is all about tensile only, right? Only we have to do tensile. But the important thing is, you want to make sure that you hold the cheese with the clips and all, and then you have to stretch it. One end can be stationary, other end can be movable, right? You stretch it like that. And this has to be done in the high temperature region, right? Yeah, 80, 90, 100 like that. Can we put it, where do we put these things in the oven? We cannot do it in the oven, right? It has only small space, right? This may be stretching like crazy, right? Our cheese may be stretching like crazy. So we need to set up something different, standalone things, where you can have a very long kind of platform where you can have oil inside that, and then you can have an external heat source, so you can heat the oil, and then you put the cheese inside the oil, and then you can stretch them. That's what we did for our develop the method like that. I didn't bring those pictures, but I thought I can explain to you how we do that. So you can measure that, and then how much it went. You can calculate the deformation, and from there you can differentiate the different types of cheeses. In the literature, we found out that this is one of the methods they used. What they did was they developed the 60-day storage time, how the cheese stretches after 60 days. They evaluated 10 days difference. And here, very interestingly, they used the same Instron machine or textural analyzer machine. So what they did was they melted the cheese, and then they put the fork there, and then they lifted the whole thing out and see the stretchability. What's the drawback of this method?
Damage of sample.
Well, damage of sample is anywhere it's going to be there. Once you heat the sample, it's damaged. Whatever method you select, it's going to be damaged anyway. You cannot really do anything about that. But what are the other issues here? Well, they are trying to mimic the consumers. What when they eat the pizza, basically it's a heated cheese. So when they are eating it, it's going to get cold. That's what they did that this way, I think. So my problem is with this method, there is no constant heat here. So depending upon how fast this cheese cooled will have impact on how much it stretches. So our method is basically we have this platform here, the oil is here, and then our sample is put it here. This is fixed, and we are moving this one. And we still use the textile analyzer only so that we can move the thing at a constant speed. Consumers may not do this constant speed thing, right? When we are eating it, some people are faster, some people are slower, so they may use a different speed and all. But at the end of the day, you can still use these kind of methods to measure the stretchability. So what is the outcome from here? As you increase the aging, the cheese softens very much, so the stretchability is less at a higher storage. So initially it's 270 centimeter, and then as you increase the aging of cheese, its proteolysis happen, protein network damages, so it becomes softer, and that's why the stretchability is getting lower, because it's become softer cheese, so you don't get that much stretch because of the protein network damage, so your stretchability will be less. So a lot of times they like to have a fresh cheese when they put it in the pizza, so that you have more stretching going on. But for the burger and other applications, aged cheese consumer prefer. So in some applications aged cheese is important, some application aged cheese is not that important. It may not serve the purpose. That's what I'm trying to tell. They also measure the yield load of the cheese when stretched. It decreased from 0.17 Newton to the 0.08 Newton. So initially it's harder cheese or elastic cheese. So yield load is higher, and it started decreasing as the storage time increased. Any other thoughts about the functional properties of cheese? No, because we use the same oil, same temperature, so conditions are still same, but it became messy, right? You are putting the cheese in the oil, and then every time after test is over, you have to take everything out, clean it out, and then do the another test for the new samples. Because the conditions are same oil, same temperature we used, so I don't think we need to worry about it. Obviously, with oil immersion, that would have had some impact on the measurement, but as long as we use the same conditions, that's what it's needed, right? At the end of the day, you are comparing your control sample and your treatment. These are all not absolute measurement. Any other thoughts anybody has in terms of functionality of dairy products? Other ways of measuring functional properties of different dairy products? What are the dairy products you guys use it here? Milk? That's a starting point. Butter, yogurt, butter, ice cream. What is it? Rabadi? What's that? Oh, okay. No, yeah. Condensed milk, yeah. Paneer, yeah. People said paneer already. So what kind of test we can use for paneer and all? It's similar to cheese, right? Whatever you do cheese, we can do the same thing for paneer. But the only thing is paneer will not melt. Exactly, because we're resting the melt, but we can use the texture profile, compression test, the viscoelastic nature of the cheese, like the paneer, things like that. I'm sure there's a lot of research published in a lot of journals, right? I mean, people publish left and right here, right, with a lot of dairy products. Yep. Okay, the question is, what makes the difference between the cottage cheese, the paneer, and then the other cheeses they make?
That melts.
Huh?
Other cheese melts.
Other cheeses melts, but the cottage cheese doesn't melt, primarily because of the processing conditions they go through while they are making these specialty products. For example, in cheese making, what do they do with cheese making? Anybody knows? I think you probably studied it, right?
Isoelectric precipitation.
Yep. So basically, you start with the milk, you heat the milk, and then you add the coagulant. When you add the coagulant, that's going to have a chemical reaction with the milk, and it's going to precipitate. So it's going to form some curd-like material, and you need to cut the curds in the right time so that you can drain the whey, and then you get the cheese. Cheese curds. You get the cheese curds, and then you press them to get the cheese and cheese blocks, and then you put the cheese block in the storage, and you store them, age them, and then you can use it. While you are doing this cheese making process also, instead of pressing it, you send them through the extruder, and that's where you form the fiber in the cheese, and that's called the mozzarella cheese. Primarily, mozzarella cheese is used in cheese making process, pizza making process, cheese making process. I am not a dairy scientist, that's why I cannot have a flow all the way through like that. So, in the pizza making, they use the mozzarella cheese. Very seldom they try to mix it with the cheddar cheese to some extent, but it's mostly mozzarella cheese. For the purpose of the color, sometimes they add the yellow cheddar cheese there, so that you have white mozzarella cheese and the yellow cheddar cheese combined together, you get the appeal, consumer appeal. So they have the golden brown cheese in the pizza. That's how they make it. And the other way, the paneer, they don't go through this extrusion process where they have the fibers and all. And at the same time, the cottage cheese, when they make it, they also go through some other unique processes where they don't form the protein structure and the fiber structure and all. So that those kind of cheese would not melt at all. And again, that is primarily function of that cheese is paneer is primarily for the meat-like product. So that it's suppose it should not melt at all, right? Otherwise, if it start melting, it became very mushy, and you don't get the paneer. It doesn't call paneer anymore. I don't know what do they call then. There's no name for that, right? nobody want to even think about that. It's going to happen like that. So those are the differences. In cheese making process, the cutting time is very, very important. Only expert people can really go through it has a lot of training. They know when to cut it, and that's when the timing is very important. A lot of people use a lot of research work. They have done a lot of ultrasound related studies to find out the right cutting time. They measure the firmness of the curd as it goes through the process, and then the firmness, when it comes to right firmness, then they cut the cheese. They cut the curd, and that's how they make the cheese.
Actually, cottage cheese is prepared from skimmed milk. That's
Okay, cottage cheese is made from skim milk because skim milk doesn't have any fat, and that makes it won't melt at all. The fat is the component which makes that cheese melting. So less fat you have, no melting characteristics because protein cannot melt itself. Very good point. Thanks for bringing it up. Any other questions? So after lunch, when we come back, we'll talk more about the measurement techniques in dairy products, and then we'll go to that. The next lecture will be on next lecture will be on the texture of measurement of texture using the sensory methods. So we'll talk more about the sensory also, what it takes to do the hardness, firmness, cohesiveness, chewiness, those kind of measurements. We'll talk about that. Other questions? One more thing is here the application of the stretchability. There's a control sample and then sample 1 and sample 2. In terms of the cheeses they prepared, control sample is unripened, reconstituted skimmed milk. And then sample 1 is standardized, ripened, reconstituted milk. And that sample 2 is unripened. So stretchability, again this is when you see this graph here, what is come to your mind? I see that points here. What kind of test it is from just looking at the data here? Sensory analysis, good point. Thank you. Niveta says it's a sensory analysis, it's not an instrument analysis because they have points. I think they probably use it a 9-point scale. So they got the 6.5, 5 here, and then 0.5 point here. So this is about the stretchability and meltability. Again, it's stretchability, it doesn't stretch that much, and control had a much higher stretching going on. Okay, I am not sure whether it's just only stretchability information. My gut feeling is it's probably stretchability and meltability combined evaluation. So the ripened cheese sample 1 will have supposed to have more melting, right? And they will have a less stretching, right? When you think about that, ripened. When you think about this data and this data, as you increase the ripening, ripened cheese has a less stretch than the unripened cheese, right? But my gut feeling is it's probably different study, not the same study, and it's something to do with the different cheeses they made. But again, these scores will be combination of both stretchability and meltability, not just only stretchability only. So that's what they are talking about here, right? Both good melting and stretching properties. When you do the sensory analysis, it's probably very difficult to really differentiate meltability and stretchability like that. And again, whether it's a trained panel or not, we don't know what kind of panel they did. So it's probably just biting it and then saying that, oh, this bite's good, so it could be melting good or stretching good and things like that. So whatever in general, whatever you can think of, I mean, from your studies or anything else. Say it again. Geldal? Well, Geldal is primarily used for protein analysis, right? I'm thinking in terms of the textural functional properties. Is there any other way we can measure these properties? I mean, Geldal is there, moisture content measurement is there, fat analysis instruments are there, which we'll be talking about this afternoon also when we look up the dairy products measurement techniques, overall measurement techniques. Anything else?
So if it is a liquid dairy product, then can we measure the consistency, smoothness?
Yeah, from sensory point of view, you can do that. And also you can do the viscosity measurement and find out whether that falls into Newtonian fluid or non-Newtonian fluid, and from there you can have the modeling going, and from there you can get the consistency index, flow behavior index, those kind of numbers. So we can do that way also. There's opportunity there for that. Oh, okay, you are talking about microstructure. Microstructure, yeah. I mean, definitely, I mean, it's always important that we do microstructure analysis and then combine that with our instrument analysis. So like dynamic rheology method. So if you do dynamic testing, so you should be able to correlate with the microstructure analysis. That people have done a lot of work on it also. So anybody can do the similar work. So that will have much more appealing results and more understanding of what is happening in the different dairy products. The question is, they measure the fat content in the Gerber centrifuge, and is there any other method for measuring the fat content of the dairy products? Anybody used any other methods? So is the Gerber method is the standard method in India? They use it.
Actually, I used in my lab. I don't know exactly. That's why I'm asking you.
Yeah, I think you have your own professional organization here, and then they have the standard methods for those kind of things, right? So I think if your lab has it, meaning that I think everybody else is using the same method, very well known method here. So in publication and all your peers will approve that, and then they accept that. But a lot of times in my lab, we don't do all those specific proximate analysis and everything, because
How they measure the fat content.
we just send the sample to the labs and we get somebody do the job, do the work, because primarily because we do not deal with a lot of dairy products. I mean, we just do our engineering
I
analysis.
want to know, is there any standard method?
Well, every region has their own standard method. Europe has their own standard method. US has a different standard methods. I think that's why you are using Gerber method, which I am not aware of it, but I think I hear that people use the same method in other labs also. So, but once you have the standard method, you just follow the standard method, right? Why unnecessarily reinvent the wheels? Because as long as the bottom line is, if you are extracting all the fat and measuring it correctly, that's all it matters at the end of the day, right? So I don't think one method is better than another method, as long as you get the right results. And at the same time, you just want to make sure that you calibrate your instrument correctly. That is very critical. If you don't calibrate your instrument, your result doesn't mean anything, because your numbers may not be right number what you are getting at the end of the day. So calibration is very, very key. And if you are working in the lab, if you are using an instrument which is not used for almost a year, don't even touch the instrument. Make sure that you get calibrated and make sure that you are getting the right numbers. Because you don't want to assume that somebody used this one last year, so it should be working fine. I don't have to worry about that. That may not be right approach. It's always expensive, because when you have to ask somebody to come and do the calibrations for you, but there are instruments you can use your standard solutions and standardize the equipment, recalibrate the instrument. You can do some of the instrument, but not all the instruments. I think it's probably less expensive here for doing those calibrations compared to US and all. US and Europe and all, it's very expensive. You won't believe that if I have a rheometer, if I want to ask somebody to come do a tune-up and maintenance, any idea how much they ask? Just for one trip, 1 day trip? Perfect. It looks like he is doing the job. So $5,000, simple as that. They will ask for $5,000. They will say $100 per hour, even driving, even walking, they charge $100 per hour. Saying that I'm starting from a hometown, 8 o'clock in the morning, I need to drive to airport and I have to take the flight. Those are all my time. Every hour counts. And 10 hour a day, coming in 10 hours, lab 10 hours, going home 10 hours, 30 hours, $100 per hour, $3,000. There you go. And then air ticket, meals and everything, another $1,000, and then another $1,000 this part and that part. Life is good. At the end of the day, $5,000 bill. So you, so I mean, it's, if you do a lot of testing and all with the instrument, you want to make sure that you calibrate the instrument, it's ready to go.